Hello friends, welcome back to my YouTube channel. In the 17th part of my discussion on adsorption, I will be discussing a numerical example. The numerical example is based on stage-wise adsorption. That is, it is based on two-stage cross-current adsorption. A numerical example based on two-stage cross-current adsorption. So this is an application of the equation that I had derived in part number 16. So basically we are going to understand the application of Freundlich adsorption isotherm to solve this numerical. In part number 15 I had solved the same in numerical, but there I had used the graphical method to solve this numerical. And in this video lecture, we are going to learn how to use the Freundlich adsorption isotherm to solve the numerical. So let us begin the discussion. Okay, to begin with, let us look at the numerical statement. A color impurity is to be removed from an aqueous solution by adsorbing it on decolorizing carbon. Experiments yielded an equilibrium data that is given in the following table. So you have this table where they have given us the equilibrium data. We have different values for the quantity kg carbon per kg solution, and then the values of equilibrium color per kg solution, which are in equilibrium with the given values of kg carbon per kg solution. They are given to us. In this case, the color intensity was measured on an arbitrary scale, and the color intensity, it is proportional to the concentration of the colored substance. It is desired to reduce the color to 10% of its original value. The original value is 9.6. So the task is, you have an aqueous solution. The aqueous solution is containing a colored impurity and we have to remove it. And how are you going to remove that? You are going to remove it by adsorbing it on decolorizing carbon. So in this case, decolorizing carbon is the adsorbent. When experiments were carried out, and these experiments, they yielded an equilibrium data which is given in this table. So you have different values for kg carbon per kg solution and equilibrium color per kg solution, which are in equilibrium with each other. The color intensity, it is measured on an arbitrary scale, and the color intensity is proportional to the concentration of the colored substance. So the value of the color intensity will tell you about the concentration of the colored substance. The objective is to reduce the color concentration to 10% of its original value. So originally the color concentration is 9.6 on an arbitrary scale, and this has to be reduced to 10% of this value, which is 0.96. 10% of 9.6 is 0.96. Okay, so based on the information that is given to us, we have to first get an equation for the Freundlich adsorption isotherm in the following form. Capital Y is equal to m into capital X raised to n. So we have to get this equation. That is, we have to get the values for m and n. This is the first task. And then the second task is, use the above equation to find the quantity of adsorbent required per 1000 kg of aqueous solution in the following cases: single stage adsorption and two stage cross current adsorption. So you have three tasks, you can say. First, we have to get this equation. That is, we have to find out the values of m and n for this particular case. So the idea is to use the experimental data to get the values of m and n. Then after getting this equation, we are supposed to use this equation to find the quantity of adsorbent required per 1000 kg of aqueous solution in a single stage adsorption, and then we have to find out the quantity of adsorbent in a 2-stage cross current adsorption. So that is what we are supposed to report at the end. First, we will have to report the equation, then quantity of adsorbent in single stage adsorption, and then the quantity of adsorbent in 2-stage cross current adsorption. So let us solve the numerical. To begin with, first of all, we will list what is given to us, that is the given data. So we have an aqueous solution that is containing a color impurity. So in this case, the quantity of aqueous solution, the case is you have an aqueous solution plus the color impurity in it. Therefore, the total mass, the total quantity of feed that we are going to handle is solution plus color impurity. Then as per our notation, L0, that is the quantity of feed that enters the operation, is amount of solution, amount of the aqueous solution plus the color impurity. So you need to understand this. Here, aqueous solution is not going to get adsorbed, neither the solvent nor the solute. What is going to adsorb is the color impurity. So in that case, solution in this case is the unadsorbed component, whereas the component that is adsorbing, it is the color impurity. So you need to understand this. The objective is to remove the color impurity. How are you going to remove it? By adsorbing it on a decolorizing carbon. So our objective is to remove or to reduce the concentration of color impurity by adsorbing the color impurity on a decolorizing carbon. So in this case, the adsorbent is decolorizing carbon. Only the color impurity and not the solution is adsorbed. So only color impurity is getting adsorbed. The solution is not adsorbed. So therefore, LS, which is the quantity of unadsorbed substance, it is 1000 kg. It is given to us. So LS is nothing but kg of aqueous solution, which is 1000 kg. The color concentration, it is measured in terms of its intensity. This is told to us. The color intensity, it is directly proportional to the color concentration. Again, this is known to us. So the quantity that is used to describe the intensity is color per kg solution. That is the substance that is adsorbed per kg of unadsorbed substance. In this case, the unadsorbed substance is solution, aqueous solution. So color per kg solution is nothing but capital Y. We know capital Y, this is weight fraction of the adsorbed substance on its free basis. That means capital Y is directly given to us. Color per kg solution. Amount of substance, amount of the adsorbed substance per kg of the unadsorbed substance. So this is nothing but capital Y. The meaning is capital Y is directly given to us. Let us move ahead. And then the color intensity, it is to be reduced to 10% of its original value. So we are going to reduce the color concentration. The color intensity is to be reduced to 10% of its original value. So the original value of the color is 9.6. That is, as per our notation, capital Y0 is 9.6. Then final value of Y, final value of the color intensity is 10% of this. So that is 0.1 times of Y0, which is 0.1 into 9.6, and that is 0.96. The equilibrium data is given to us. So we have different values of kg of carbon per kg of solution. It is not in an appropriate form. We will have to convert it to capital X. So we will be doing that. And then the other quantity that is given to us is equilibrium color per kg of solution. So this itself is Y, capital Y. So there is no need of any change in this quantity. You can directly use it because it is capital Y. What are we supposed to find? First, we are supposed to get an equation for the Freundlich adsorption isotherm, which is of the following form. Capital Y is equal to m into capital X raised to n. And then we are supposed to get fresh carbon required in a single stage operation. Then fresh carbon required in a two-stage cross current operation. And since you are using fresh carbon over here, since fresh carbon is used, X naught is 0. That is concentration of the solute, or in this case, the concentration of color in the entering adsorbent phase, it is 0. So that's why capital X0 is 0. The reason is we are supposed to use fresh carbon. So first we will be getting an equation of this form. Capital Y is equal to m into capital X raised to n. And for getting this equation, we are going to use the experimental data. And then we will use this equation to find the quantity of carbon or the quantity of adsorbent required in a single stage operation and then in a two-stage operation. We are using fresh carbon. The meaning is capital X0 is 0. So let us move ahead. What would be the approach for solving this? First, we will change the equilibrium data to an appropriate form. And then the equilibrium color per kg of solution, it is capital Y. So we are going, it is directly given to us. So we will use as it is. And then the other quantity, which is kg of carbon per kg of solution, we will have to convert it to equilibrium color per kg carbon, which is nothing but capital X. So in this case, the task is to convert kg of carbon per kg of solution, which is given to us, to equilibrium color per kg carbon, which is capital X. So in this way, we will change the given equilibrium data into an appropriate form. Then get the equation for the Freundlich adsorption isotherm. So capital Y is equal to m into capital X raised to n. And then once you get the equation, we will use the equation to find the quantity of adsorbent required in the two cases, single stage operation and two-stage cross current operation. So this would be the approach for solving this numerical. Let us move ahead. Now let us solve it. First, as I said, we will be converting the equilibrium data to an appropriate form. So you have this table. This is given to us. Now, if you look at the first two columns, so kg carbon per kg solution. So in 1 kg of solution, if you increase the carbon content from 0 to 0.001, that is, you are adding 0.001 kg of carbon to the solution, what happens to the color? The color reduces from its original value 9.6 to 8.6. That is when 0.001 kg of carbon is added to 1 kg of solution, the color concentration in 1 kg of solution reduces from 9.6 to 8.6. So we will use this for finding X, capital X. So kg of carbon per kg of solution, if it increases from 0 to 0.001, that is, you are adding 0.001 kg of carbon to the solution. When you do that, the equilibrium color per kg solution it decreases from 9.6 to 8.6. It decreases from 9.6 to 8.6. That is, equilibrium color adsorbed per kg of solution would be the difference between these two. That is 9.6 minus 8.6, which is 1. So all this is happening in 1 kg of solution. So that's why you have equilibrium color adsorbed per kg of solution is the original value minus the value that is resulting when 0.001 kg of carbon is added to the solution. So it is 9.6 minus 8.6, which is equal to 1. So therefore, if I take this ratio, equilibrium color adsorbed per kg solution to kg carbon per kg solution. So what is going to happen? Kg solution, it will be getting cancelled, and you are left with equilibrium color adsorbed per kg carbon. So this is equilibrium color adsorbed per kg carbon. This comes out to be 1000. And if you look at this quantity carefully, you will come to know that equilibrium color adsorbed per kg of carbon is nothing but capital X. That is, capital X is equal to 1000. That means in order to get capital X from the given data, we will have to do this calculation. So for first, when you are adding 0.001 kg of carbon, the equilibrium colored adsorbed per kg carbon comes out to be 1000. And then in the second row, you have equilibrium color per kg solution, and that is nothing but capital Y. So capital Y is directly given to us. Let us move ahead. Okay, so now let us convert the entire data. So you have different values of kg carbon per kg solution, and then we have various values for equilibrium color per kg solution. This is nothing but capital Y, and then we have to get different values for capital X, that is equilibrium color adsorbed per kg carbon. This is nothing but capital X. So these are the values that are given to us. I am collecting all those values. And first, when you are increasing, when you are adding 0.001 kg of carbon, the color is reducing from 9.6 to 8.6. So I am showing the calculation over here. So capital X is 9.6 minus 8.6 divided by 0.001. That is 1 upon 0.001, which is 1000. And then let us go to the next reading. That is, when you are adding 0.004 kg of carbon, the color intensity reduces from 9.6 to 6.3. So in this case, capital X will be 9.6 minus 6.3 divided by 0.004, which is 3.3 divided by 0.004. That is 825. Then for the next reading, when you add 0.008 kg of carbon, the color intensity reduces from 9.6 to 4.3. So capital X will be 9.6 minus 4.3 divided by 0.008. That is 5.3 divided by 0.008. That is equal to 662.5. Then for the next reading, capital X will be 9.6 minus 1.7 divided by 0.002. That is equal to 7.9 divided by 0.02, which is 395. And finally, 9.6 minus 0.7 divided by 0.004, which is nothing but 8.9 divided by 0.04, which comes out to be 222.5. So in this way, we get different values of X. And now we have to plot these, we have to use these values to get the equation for Freundlich adsorption isotherm. So let us move ahead. So I have collected all the values of capital X and capital Y, which we will be using. So I have just told you how to get the values of X. So you have various values, 9.6. I'll just take all the values, and then these are the calculated values for capital X. Now let us complete the first task. What is that? We have to get an equation for the Freundlich adsorption isotherm. The required form is capital Y is equal to m into capital X raised to n. So I will put it in a proper form. So for that I will take logarithm on both the sides. So in this case, the task is to get values of m and n. To get the equation is nothing but to get the values of m and n. So as I said, I will take logarithm on both the sides. So it will be ln of y is equal to ln of m into capital X raised to n. Then on the right hand side, I will use the logarithmic identity. The ln of y is equal to ln of m in plus ln of x raised to n. So here I have used this identity. Ln of m into n is ln of m plus ln of n. So I have used this identity to get this equation. In the next step, I will use another logarithmic identity. What is that? The identity is log ln of x raised to m, or let me use some other notation. So the logarithmic identity is ln of a raised to b is equal to b into ln of e. So I will use this identity in the next step. So it is ln of y is equal to ln of m plus n into ln of x. I have used this identity. So let me erase it. Okay. So that is, I have just rewritten it in a different form. So it is ln of y is equal to n into ln of x plus ln of m. Now this equation, the last equation that we got, ln of y is equal to n into ln of x plus ln of m. So this equation is of the form y is equal to mx plus c, which is an equation of a straight line. So in this case, y is ln of y, the slope is n, and the intercept is ln of m. So that means we can get the values of n and m if you plot this graph. Which graph? On the x-axis, on the y-axis, we can plot ln of y, and on the x-axis, we can plot ln of x. So you will be getting a straight line, and the slope of this straight line will give us n that we need, and the intercept made by the line on the y-axis will give us ln of m, and then from the value of ln of m you can get m. So in this way you can get values of m and n, and that will complete the first task. We will be getting an equation of this form: capital Y is equal to m into capital X raised to n. So I hope the concept is clear to you. We have put the required form of equation into a straight line equation, which we will be plotting. The plot will be in terms of the quantities that are given to us. Now let us plot this graph. So equation, we are getting equation for the Freundlich adsorption isotherm. So we have different values of y, and we need logarithm of these values. So in the next column, I will collect all logarithm values. So you have different values. Ln of y, you get these values. And then we have different values of x. and we need logarithm of x. So I have collected all the logarithmic values, logarithm of x values that we have got, and now we will be plotting this data. You forget about the first entry. We will be plotting the remaining data to get the straight line. The slope of the straight line is going to give us n, and the intercept made by the line on the y-axis, it is going to give us the value of m. So I will be plotting the graph. So on the x-axis, I have chosen this scale. On x-axis, I will be plotting ln of x, and on y-axis, I will be plotting ln of y. Because one of the value for ln of y is negative, and the intercept that I will be getting for the line, it will be on the negative y-axis. So that's why I have included the negative y-axis in the graph. So if you plot ln y versus ln x, you will be getting a straight line like this. Now I will extend this straight line so that I can get the intercept, because I will need the intercept in my calculation. So for this line, let us first find out slope. Slope of the line will directly give us the value of n. So for this, I will consider a point, any point. You can consider a different point, no problem. I have considered this point. The coordinates of this point are 2.2 and minus 5.8. And then I will consider another point over here, because in order to find out the slope, I will need 2 points. The other point I am considering over here. What are the coordinates of this points? This point, the second point, they are 1.6 and minus 6.8. The slope is y2 minus y1, or y1 minus y2 divided by x1 minus x2. So n, slope is nothing but n. So n will be equal to minus 5.8 minus 6.8 divided by 2.2 minus 1.6. So that is n will be equal to minus 5.8 plus 6.8 divided by 0.6. That is nothing but n is 1 upon 0.6, which gives us n as 1.67. So in this way, we get the value for n. Now let us get the value for m. So for that, we need intercept, that is ln of m. So intercept on the y-axis is over here. And if you look at the graph, it is minus 9.5. So intercept, which is ln of m, this is minus 9.5. That is, m will be equal to 7.49 into 10 to the power minus 5. So in this way, we get values for m, n and m. So therefore, the equation for Freundlich adsorption isotherm, it will be capital Y is equal to m, which the form is capital Y is equal to m into x raised to n. And now we know the values of m and n. So the equation will be capital Y is equal to 7.49 into 10 to the power minus 5 into capital X raised to 1.67. So that completes the first task. We have got the equation for Freundlich adsorption isotherm. Now let us move on. So this is one thing. Now let us find out the quantity of adsorbent that is required in single stage adsorption operation. So I will show you the operation. So the feed is L0, Ls, capital Y0. The entering adsorbent is S01, SS1, X0. And the outgoing adsorbent phase is S1, SS1, capital X1. I have talked about it in my earlier discussions. Link to the playlist of all my video lectures on adsorption. It is available in the description section. And then finally you get the solution out of stage number 1. Now equation of the operating line, we know it is y1 minus y0 upon x1 minus x0 is equal to minus ss1 upon ls, single stage operation. So for the derivation of this equation, you can refer my discussion on single stage adsorption. So when you are using fresh adsorbent, x0 is 0. So in that case, the equation will be capital Y1 minus capital Y0 divided by capital X1. That is equal to minus SS1 upon LS. Now, the equation of the equilibrium curve is, we have got this equation. Capital Y is equal to 7.49 into 10 to the power minus 5 into x raised to 1.67. So that means you have this equation is of the equilibrium curve, and the operating line for a single stage operation looks like this. So this point is x0, y0, and this point is x1, y1. What I want to tell you is x1, y1, this point, it lies on the operating line, and at the same time it lies on the equilibrium curve. That means the point x1, y1, it should satisfy the equation of the equilibrium curve. So the point x1, y1, it lies on the operating line, and it also lies on the equilibrium curve, and therefore it should satisfy the equation of the equilibrium curve. Therefore you have this equation, capital Y1 is equal to 7.49 into 10 to the power minus 5 x1 raised to 1.67. Let us move ahead. So we are looking at the calculations for single stage operation. We got this equation, capital Y1 is equal to 7.49 into 10 to the power minus 5 into x1 raised to 1.6. Now the final y in this case, which we are going to get in one single stage operation, it is 0.96 because it is 10% of the original value. So in this case, capital Y1 is 0.96. So therefore, if you use this in this equation, it will be 0.96 is equal to 7.49 into 10 to the power minus 5 x1 raised to 1.67. That is 0.96 divided by 7.49 into 10 to the power minus 5. That is equal to x1 raised to 1.67. That is 12825.34 is equal to x1 raised to 1.67. This division is 12825.34. That is x1 is equal to 12825.34 raised to 1.67 in order to get x1. So therefore x1 will be 288.35. So for single stage operation, the value of x1 is 288.35. Now we are going to use this value to get the quantity of adsorbent. So for that, again we will need the equation of the operating line. It is y1 minus y0 upon x1 minus x0, that is equal to minus ss1 upon ls. When you are using fresh adsorbent, x0 is 0, so x0 is 0, then y0 you know it is 9.6, y1 is 0.96, x1 we got, that is 288.35, and ls is 1000 kg. So if you use these values in the equation, it will be 0.96 minus 9.6 divided by 288.35 minus 0, that is equal to minus ss1 upon 1000. That is minus 8.64 divided by 288.35, that is equal to minus ss1 by 1000. That is 0.03 is equal to ss1 by 1000. That is ss1 will be equal to 0.03 into 1000. That is ss1 is equal to 30 kg. And so this is the quantity of adsorbent that will be required in single stage operation. So that completes our second task. First task, we got the equation for the Freundlich adsorption isotherm. And the second task, we got the quantity of adsorbent that will be needed in a single stage operation. Now let us go to the last task, which is to get the quantity of adsorbent in two-stage operation. So let us move ahead. Two-stage operation, I will show the task is, in two-stage operation, the reduction in color from its initial value 9.6 to the final value, which is 0.96, it is to be obtained in two stages. So you have stage number 1, feed will be entering into stage number 1. Some quantity of adsorbent will be used in stage number 1. Then we will be having some color impurity adsorbed on this quantity. The liquid solution will then be taken to the second stage, where it will be contacted with new batch of adsorbent, which may have a different quantity, and then some of the color impurity will be adsorbed in this stage, and finally you will be getting a solution which will have a reduced concentration of color impurity in it. So that is the task. So in this case, the challenge is to get the value of y1, because y0 is known to you, y2 is known to you, y1 and then x1, they are not known. So the important task is to get these values. And in my earlier discussion in part number 15, where I had discussed the same numerical, but I had solved that graphically, there I had told you how to use trial and error method to get these values. If you have not yet seen that video, you please watch it. The link to the entire playlist is available in the description section. So in this case, we are going to get these values by using an equation that I had derived in my previous lecture, part number 16. So that is what we will be doing in this case. So let us move ahead. So the important task is to select the value of y1. And how are you going to select it? It is to be selected so that the total amount of adsorbent required is minimum. So we are going to choose that value of y1 which will give minimum total amount of adsorbent. Total amount, by total amount I mean amount of adsorbent required in stage 1 plus amount of adsorbent required in stage 2. Let us move ahead. Now, as I said, I will be using this equation. I had derived it in the previous video lecture. So capital Y1 by capital Y2 raised to 1 by n minus 1 by n into capital Y0 upon capital Y1, that is equal to n minus 1 upon n. So in this case, n is known to us, Y2 is known to us, Y0 is known to us. The only unknown is Y1. So the task is, you have to solve this equation. You have to solve this equation by using an appropriate method to get the value of y1, and we will be doing that. So you have this equation, capital Y1 by capital Y2 raised to 1 by n minus 1 upon n into Y0 upon Y1, capital Y0 by capital Y1, that is equal to n minus 1 upon n. So in this case, y2 is the final value of y, which is 0.96. Then y0, that is the initial concentration, is 9.6. Then n, we have obtained it earlier, 1.67. So that means the equation becomes y1 divided by 0.96 raised to 1.67 minus 1 upon 1.67 into 9.6 divided by capital Y1, that is equal to 1.67 minus 1 divided by 1.67. So that is y1 divided by 0.96 raised to 0.6, 1 upon 1.67 is 0.6, minus 9.6 upon 1.67 is 5.7. So it is minus 5.75 divided by capital Y1, and this is 0.4. So this is y1 raised to 0.6. I have separated the power, divided by 0.96 raised to 0.6. That is equal to 5.75 divided by capital Y1, that is equal to 0.4. That is capital Y1 raised to 0.6 divided by 1.025. 0.96 raised to 0.6 is 1.025 minus 5.75 divided by capital Y1, that is equal to 0.40. That is y1 raised to 0.6 divided by 1.025 minus 5.75 divided by capital Y1 minus 0.40, that is equal to 0. That is, I have got an equation in terms of y1. So this is an equation in y1, and we need to solve it for getting the value of y1, and you can use any appropriate method. In my discussion, I am going to use Newton-Raphson method to get the value of y1. So you can use any other method for finding the value of y1. So in order to tell you how you get the value for y1, I am using Newton-Raphson method, numerical technique. So we got this equation. y1 raised to 0.6 divided by 1.025 minus 5.75 divided by capital Y1 minus 0.40, that is equal to 0. Now I will be denoting, this is some function of y1, so I am going to call it as function of y1 is equal to y1 raised to 0.6 divided by 1.025 minus 5.75 divided by capital Y1 minus 0.40. To solve, f of y1 is equal to 0. That is, in order to solve this equation, we are going to use the Newton-Raphson method, as I said earlier. And what is the method? To get the new value for y1, the new value, I am denoting it as y1 n plus 1 is equal to old value of y1. Old value is, I have denoted it as capital Y1 n minus the function evaluated at old value, that is y1 n, divided by derivative of the function that is evaluated at the old value, y1 n. So in order to use this equation, we will have to first get the derivative. So f dash y1, his derivative of this is, it is easy to get. So it is 0.6 y1 raised to 0.6 minus 1 and divided by 1.025 plus derivative of 1 upon capital Y1 is minus 1 upon capital Y1 square, and minus becomes plus. So that's why you have plus 5.75 divided by Y1 square, and this is a constant, so this it will be 0 in the derivative. So f dash of y1 is 0.6 y1 raised to 0.6 minus 1 divided by 1.025 plus 5.75 divided by y1 square. So that is f dash of y1 is equal to, I will simplify over here, 0.585 y1 raised to minus 0.4 plus 5.75 divided by y1 square. Now, in order to start the solution, we will have to use the guess value, and you have to guess the value, and the guess value I will be using is, let us say that in the first stage the concentration of the color reduces by half, that is from approximately half, from 9.6 to 4.5. So this is approximately half of the initial concentration. So I have done the calculations. So I have used, starting with the initial case, I have found out the function at that value, then derivative at that value, and finally I have got the new value for y1. So first guess value is 4.5. Function at this value is 0.83716. Derivative of the function at this value is 0.62. And the new value for y1 is 3.15. So in the next iteration, I'm going to use this as the old value. So y1, now it is 3.15. Function at this value is minus 0.19907. Derivative of the function is 0.97. And new value for y1 is 3.35. And then in the next iteration, with the initial value 3.35, the function at this value is minus 0.0081. Now we are going close to 0. The function will become 0 at the exact root of that equation, that is at the exact value of y1. So function is minus 0.0081, and derivative of the function is 0.89, and the new value for y1 is 3.36. In the next iteration, if I use 3.36, the function is minus 3.3 into 10 to the power minus 6, very close to 0. The derivative of the function is 0.88, and the new value is again 3.36. And then in the next step, if I use the value, the function becomes still smaller. It is very close to 0. And the derivative of the function, there is no change in it. And the value of y1, again, there is no change in it. So that means I have arrived at the solution. I have got the value of y1 that will satisfy this equation. And what is that value? 3.36. So in this way, you can get the value of y1, the important task. Let us move ahead. You can use any other method for solving this equation. That is not a problem. So we got y1 as 3.36. The equilibrium curve is given. The equation of the equilibrium curve is y is equal to 7.49 into 10 to the power minus 5 x raised to 1.67. Now point x1 y1, it lies on the equilibrium curve. I have already talked about it, how it happens. Therefore this point should satisfy the equation of the operating line. So it is capital Y1 is equal to 7.49 into 10 to the power minus 5 x1 raised to 1.67. That is 3.36 is equal to 7.49 into 10 to the power minus 5 into x1 raised to 1.67. That is x1 raised to 1.67 is equal to 3.36 divided by 7.49 into 10 to the power minus 5. That is x1 raised to 1.67 is 48064.1. That is x1 is equal to 48064.1 raised to 1.6 raised to 1 upon 1.67. That is x1 is equal to 636.04. Now for the first stage, the equation of the operating line is capital Y1 minus capital Y0 divided by capital X1 minus capital X0. That is equal to minus SS1 upon LS. Y0 is 9.6, X0 is 0 because you are using fresh adsorbent. LS is 1000 kg. So therefore 3.36 minus 9.6 divided by 636.4. X1 and Y1 we have found out. 636.4 minus 0 is equal to minus SS1 by 1000. That is minus 6.24 divided by 636.4. That is equal to minus SS1 by 1000. That is minus 0.00981 is equal to minus SS1 by 1000. That is SS1 is equal to 0.00981 into 1000. That is SS1 is equal to 9.81 kg. So this is the quantity of adsorbent that will be needed in first stage. Now let us do the calculations for second stage. So we have the final value for y is 0.96. That is in this case capital Y2 is 0.96. And the equilibrium curve equation is y is equal to 7.49 into 10 to the power minus 5 into x raised to 1.67. Now the point x2 y2 will be lying on the equilibrium curve. Therefore it should satisfy the equation of the equilibrium curve. So that's why you have capital Y2 is equal to 7.49 into 10 to the power minus 5 x2 raised to 1.67. That is 0.96 is equal to 7.49 into 10 to the power minus 5 into x2 raised to 1.67. That is x2 raised to 1.67, that is equal to 0.96 divided by 7.49 into 10 to the power minus 5. That is x2 raised to 1.67 is equal to 12825.34. That is x2 is equal to 12825.34 raised to 1 upon 1.67. That is x2 is equal to 288.35. Now for the second stage, the operating line equation is capital Y2 minus capital Y1 divided by capital X2 minus capital X0. That is equal to minus SS2 by LS. That is Y2, we know Y2 is 0.96, Y1 is 3.36, X0 is 0. Since you are using fresh adsorbent, LS is 1000 kg. So it will be 0.96 minus 3.36 divided by 288.35 minus 0. That is equal to minus SS2 by 1000. That is minus 2.64 divided by 288.35. That is equal to minus SS2 by 1000. That is minus 0.00916 is equal to minus SS2 by 1000. That is SS2 is equal to 0.00916 into 1000. That is SS2 is equal to 9.16 kg. That is the quantity of adsorbent required in the second stage is 9.16 kg. So in this way we get the quantity of adsorbent required in the second stage. So finally we will get the total amount of adsorbent required in both the stages. So that is SS is equal to SS1 plus SS2. SS1 is 9.81 kg, SS2 is 9.16 kg. So yes, the total amount will be 9.81 plus 9.16, which comes out to be 18.97 kg. So the total amount of adsorbent required in a two-stage cross-current operation is 18.97 kg. If you remember, with single-stage operation, it was 30 kg. Now you can compare the results that we have obtained in this numerical with the results that were obtained in part number 15. So that is, you can check that. So with this, I end my discussion. We have completed all the tasks. We have got the equation for Freundlich adsorption isotherm. We found out the amount of adsorbent required in single stage operation, and then we found out the amount of adsorbent required in a two-stage cross current operation. So with this, I will end my discussion for today's video. Thanks for watching this video lecture. Do subscribe to my channel. Tell your friends to subscribe to it. Hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day. Bye-bye, and hope to see you soon in my next video lecture. In my next video lecture, I'll be starting my discussion on multi-stage counter current adsorption. So thank you. Have a nice day. Bye-bye.